So if you have any relation, in order to get the inverse of that relation, you have to interchange or change or exchange the x and the y values. So let that be something that you just sort of, like one should trigger the other, right? And in order to find an inverse, you have to exchange x and y. Okay, and if you exchange x and y, you've essentially found the inverse. So if in going from a relation to the inverse, I'm swapping everything that's x with everything that's y, right? Everything gets swapped. So when we talk about domain and range, remember, domain is all of the possible x values that apply to a relation, and the range is all of the possible y values that apply to a relation. So when I interchange x and y, all of that will get switched as well. So the domain of the domain of the relation will become the range of the inverse and vice versa. Okay? So the domain will become the range and the range will become the domain. So take a look at this relation, okay? And these should have curly brackets around them. Take a look at this relation. We want to find the inverse of it. We're not concerned about whether or not this is a function. We just want to find the inverse of it. And you literally take each and every coordinate point and just swap x and y. So 1, 3 will become 3, 1. Then 3, 6. Then 0, 6. Then 0, 1. I'm sorry, 6, 0. Right? Okay, now what we're going to do is we're going to graph the original and the inverse. So first I'm going to graph the original in black. Okay, so it's 1, 3.
What's that line on the...
Okay, please raise your hand. Yep, thank you. Okay, so then 6, 3. Okay, 0, 6. Oops, 0, 6. And then 1, 0. Okay, right there, right? So those were the original. Now in purple, I'm going to do the inverse. So the first one is 3, 1. The next one is 3, 6. 1, 2, 3, 4, 5, 6. The next one is 6, 0. And then the next one is 6, 3. No, 1, 0, 1. Okay? Okay, so take a look at what happened. Take a look at each purple and each black dot. Do you see how every single one of them, if you look at this red line, this red line is the line y equals x, right? Do you see how if you look at that red line, each black dot has a mirrored image in that red dot to a purple one, in that red line to a purple one. Do you see that? This black one has a mirrored image to a purple one. This black one has a mirrored image to a purple one, and this one has a mirrored image to a purple one. Do you see that? So what are the coordinates of each of these? If I take this first pair, right, I have 1, 0, 0, 1. The second one, this is 3, 1, 1, 3. So do you see what happens when I interchange x and y? Every single point gets reflected in y equals x. So we've learned about reflection in the x-axis. We've learned about reflection in the y-axis. But really, you can reflect around any line. And when something is reflected around the line y equals x, then it becomes the inverse of the original. Okay? All right. So So that is what it says here, that f of x equals x represents the reflection of the function and its inverse. So what is the domain and range of the original? So the domain of the original is all the x values, right? And I have 0, 1, and 6, correct? And what is the range of the original? 3, 0, 3, and 6. Everybody agree? And now let's look at the domain of the inverse. What's the domain of the inverse? 0, 3, 6. And the range of the inverse is 0, 1, 6. Okay? So look at what happened. The domain of one became the range of the other, and the range of one became the domain of the other. Cool? Okay. So what if you have a function? To find the inverse of a function, first of all, we learned that function notation is this, f of x. The symbol for the inverse of x is this, f to the power of minus 1 of x. That's read as the inverse of f of x, or f inverse of x, okay? You never say f to the minus 1, please. It's either inverse f or f inverse. Okay, so how do you find it? First of all, if it's given in terms of f of x, just rewrite f of x as y, because, you know, they're kind of synonymous, right? Then exchange x and y in the equation, solve for y, and then in the end, you have to replace y with f inverse. 85% of the time, students do this, and then they forget to replace it with f inverse, and it's automatically at least minus 1, right? Okay, so let's do this. Okay, we're going to find the inverse of each function, and then we're going to graph both of them. So first of all, I have f of x equals this. So first, let's write it as y equals half x plus 3. Haven't done any math yet, right? Just rewrote f of x as y. Now, let's exchange. Make this x equals 1/2 y plus 3. Okay? Still haven't done any math. I just swapped x and y. Now I need to solve for y, which you've been doing since your algebra days. Let's subtract 3. This is so exciting. Okay, x minus 3 is equal to half y. Multiply everything by 2. So 2x minus 6 is equal to y, but I can't leave it like that. Now I have to rewrite this as f inverse of x is equal to 2x minus 6. Okay? Now, let's graph the original. I'm going to graph the original in purple. Half x plus 3, this is a, linear function, so y-intercept is 3, up 1 over 2, right? I just want to put in some more points. That's how that looks. Let's label this f of x so we know, because we're professionals, we're in honors. And now, let me graph the other one in blue. Okay, the f inverse in blue. So y-intercept is negative 6. I go up 2 over 1. Up 2 over 1. Okay. That's how that looks. Okay, and do you see how the blue and the purple are a mirrored image of each other along this red line? Yeah? Okay. Look at the slope, right? Look, this was 1/2, this is 2 over 1. You see how the rise over the run got switched, right? Because the x and the y's got switched, okay? All right. So next, let's do this one. F of x is x squared plus 3, so y is x squared plus 3. Switching, I get x equals y squared plus 3. Subtract the 3. Take a square root of both sides. So I get y equals plus or minus. Don't forget that plus or minus. The square root of x minus 3. that means f inverse of x is plus or minus the square root of x minus 3. I'm going to box that in blue. Okay, let's graph these. So the original, x squared plus 3, everybody's favorite shape, parabola, right? Vertex is at 3, 0. And then I go over 1, up 1, over 2, up 4. Okay, that does not look like a pretty parabola. I need to make this pretty. Okay? Okay, now take a look. That's the parabola, correct? Okay, now I'm going to graph this. This is actually two separate functions. One is f of x is positive the square root of x minus 3. So when I have the square root of x minus 3, right, the minus 3 shifts it to the right 3 units, remember? So essentially, here is what I have. I have f inverse of x is equal to the square root of x minus 3 and negative the square root of x minus 3. So I'm going to graph the top one first. That goes here. That's the end point, right, or the starting point. Now, I go up 1. I go over 1, and I have to go up the square root of 1. And then if I go over 4, I go up 2. So that's how that looks. Now I'm going to graph the bottom minus the negative root. So I'm graphing two square roots in one problem. Okay? What's the starting point for this one? 3, right? But where does the first point go? If I'm at x equals 4, where's the y going to be? Down 1, negative 1. And then here, this is going to be down 2. So that's how that looks. So look, this is f inverse of x. The first one was f of x. Which one? Okay, graphing this is what we did in section 2. Oh, yeah. Okay, maybe watch section 2 and then we'll go back over it. Okay, but take a look at the purple and the blue. Do you see how one is a mirror image of the other in the right? So again, that's how we can see that they're inverses. Huh? You don't remember graphing square roots in section 2? Yeah. Yeah, but now, okay, so now I'm graphing 2 in one set of axes. You know how to graph this, yes? Yes, you do. You forgot from section 2? That was literally 2 days ago. Okay, maybe, right. So you can go back and remember because you still have access to the notes. Okay, so take a look at what happened here. Look at the inverse for the first one, the blue line. Is that a function? Yes? Okay. Look at the inverse here, the blue one. Is that a function? No, not a function. Okay, so let me tell you why. Let's take a look at the original. Well, this is not a function because it doesn't pass the vertical line test, right? Okay. Let's look at the originals now. We know the vertical line test. Now let's take a look at the horizontal line test. This is new. Look at this original purple function. Would it pass a horizontal line test? Yeah. Would each horizontal line pass the graph only once? Yes. So its inverse will be a function. Does this parabola, the purple parabola, pass a horizontal line test? No. It does not. So its inverse will not be a function. So let's go over here. A function has an inverse function only if the original passes the horizontal line test. Okay? And if it passes the horizontal line test, it is called a one-to-one function because for each y value, there is only one x value. If it's not one-to-one, for each y value, there are two x values. Okay? Okay. All right, now, verifying inverses. Take a look at this word. Verifying. Okay? This does not say showing. It does not say illustrating. It says verifying. And that word in math has a special significance. And when you have to verify something, there is usually like a formal process that goes with it. Okay? All right. So how do we verify if two things are inverses? Well, here we go. F and G are inverses if and only if f of g of x is x and g of f of x is x. It's actually kind of simple and it's super cool. So if you have two functions, it says determine whether they're inverse functions. When I write them on the test, it'll say verify that the two are inverse functions. So here's what you have to do. You have to find f of g of x. You have to find g of f of x. You have to get x as an answer for both of them. Then it's true. It's an all or nothing deal. So let's do one of them. So first I want to find f of g of x. Okay, I'm going to use this notation today because as honor students, we want to be equally comfortable with all the notations. F of g of x. So what's happening? What's the outside function in this case? F. So g is going to go inside of f, correct? Okay, so it's going to be, so it's going to go inside of the x. So it's going to be 3 times 1 over 3x minus 3 plus 9. So distribute, this is like one of the most satisfying things we do in math, right? So we get x minus 9 plus 9. What does that reduce to? X. Okay, halfway there. Now I want to find g of f of x. This time, sorry, I was using the other notation. I forgot. G of f of x. Okay, this time I want to put g inside of f. The other way around. F inside of G. You know, okay, so I had coffee right after I had my lunch and I realized it must have been decaf or something because it like hasn't even hit me yet. Okay, so now I'm going to put, okay, so it's going to be 1 over 3 times 3x plus 9 minus 3. Does it work? It's so awesome. X plus 3 minus 3, it equals x. Yes, so they are inverses. Now, people always ask me, does it have to be x and x, or can they just be the same thing? Like, can it be 0, 0, 2x, 2x? No, it's got to be x and x. Another thing students always ask me, well, can't I just get f of x, find the inverse, and show that it equals g of x? See, that's not verifying. That's just illustrating or showing and so on. That was your question, wasn't it? I get it every year. Every year. Okay. All right. So let's do here f of g of x. Huh? No, we're not going to be, right? We're going to be positive here. So 2 times. Now let's put in the g of x. Okay, square it. Minus 1. Remember, do the exponent first. So 2 times x plus 1 over 2 minus 1. What now?
Is it like 2x plus 2 over 2?
I can cancel the 2's there, right? So I get x plus 1 minus 1, which is equal to x. Halfway there. Yeah.
Does the root go away when you square because it's...
Because, right.
A square root.
The square of a square root, it just goes away. Okay, so g of f of x, I'm going to now put f inside of g. Okay, so I have a square root. F is 2x squared minus 1 plus 1 over 2. Right? What happens now? 2x squared over 2. Oh my gosh, the 2's go away. It's just the square root of x squared, which is just x. Look at that. Yes. Okay? So I do have to like see the work for this one. Okay? All right. So go ahead and do the next one. and I'm gonna walk around to check it out. All right, so f of g of x. Start with that one. In this case, we do the first one, and you see that you're not getting x by any means. I'll even stop right here. I don't have to continue all the way, because if it fails the first part, then that's it, right? So this is a no. It's x plus 7. Okay, so now, so that's it. You don't have to continue, okay? Oh, how come it's frozen? Okay. So next, use the horizontal line test to determine whether the inverse of each function is also a function. Use your graphing calculator if necessary. So take a look at this one. Before you reach for your calculators, x cubed minus 4, right? Do we know what, this is an odd function, so it's going to look like this, right? Does this pass the horizontal line test? Yes, right? It passes the horizontal line test, right? Because each horizontal line will only pass the graph one time. So yes, it has. Okay, so the terminology for this, right? You can either say its inverse is also a function, or in short, we say, yes, this has an inverse function, right? So both of them are used. Okay, so the next one, x cubed plus 2x minus 7, what do you think? Okay, so this one, it can get a little tricky, right? Because depending on this term, right? Depending on this term, if you've got another term with an x, okay, so it could either, it could either look like this, or sometimes they can look like this, right? In which case it will not be a function, like the inverse will not be a function, depending on this term, because in the middle, this adds like extra sort of linear things. So I would suggest, for those, you're more than welcome to use your calculator, graph it on your calculator, and you can see. This one actually go ahead and graph it and see if it does have an inverse function. So I want you guys to be able to see it. Oh, hang on. So if we go ahead, graph this one, y equals negative 2x cubed plus 8x minus 1. So this one, it does, right? The x cubed plus 2x minus 7, it does. What about that one? Negative 2x cubed plus 8x minus 1. That's a definite no, right? Do you guys see that? I think I had put that on one of your tests because it's in my calculator, so I must have tried it for one of your tests to get like minimum or maximum or something, right? Do you see how this clearly does not pass the vertical line test? So if you have a cubic function, if it's a simple one like this where you have a cubic function plus or minus a constant, you can easily figure it out that it's going to look like this. But when you've got an extra linear term in there, I would like try it out, okay? Because it'll have a little bit of a spike. Okay, so that's for the lesson.